Okay, so let me start with a very broad introduction. There we go, perfect. So what is the big picture question we're interested in? We're interested in understanding the properties of complicated driven dissipative systems, okay? So this is a theorist's view of a driven dissipative system. I start with some degrees of freedom that are described by a Hamiltonian. So maybe this is a collection of interacting qubits. The Hamiltonian might already be complicated. These qubits could be interacting. There could be crazy things in the Hamiltonian. We then might make life even more interesting by adding driving in some form. The driving could be a time dependence to the Hamiltonian. The driving could be terms in the dynamics that can add excitations to the system. And then we balance that driving with some dissipation, right? Maybe that's lost. Particles and excitations can leave the system. Maybe it's some sort of dephasing. So in general, when I have this mix of complicated different ingredients, if I just turn these things on and let the dynamics go, I'm going to end up in generically some non-thermal equilibrium state, right? That involves the interplay of all three of these ingredients, right? So what's a general question I can ask, right? What is the nature of that non-equilibrium steady state? Does it have quantum features? Is there new interesting many-body physics? Could I do something useful, right, with that steady state? Okay, so this is a cartoon. At some level, almost any experiment in quantum information physics in one way or another has all three of these ingredients in it, right? Let me just give one specific experimental example that will connect to something I'll tell you more about later in the talk. So there are a class of experiments that try to realize this interplay of these three ingredients in a many-body regime, not necessarily to do something useful for quantum information, but to study interesting many-body physics. Okay, so this is a somewhat recent experiment from the Google superconducting qubit team. What they did in this experiment is use a chain of transmon qubits, that's these circles here, to investigate some phenomena that has been vexing a lot of condensed matter physics. If I have an interacting spin chain, how do excitations move through the chain? Do they move ballistically? Do they move diffusively? Do they do something else? So in this Google experiment, they were able to, with the digital quantum simulation, simulate driving and dissipation, where there's dissipation just at one end of the chain, there's driving at the other, the excitations can hop along the chain, they can interact. They could look at how excitations move through the system. Okay, so a generic question is, if they just turned on this experiment and you wait, what would the steady state of all these qubits look like? Can I say something about that, even if the interactions, the dynamics of the qubits are complicated? Okay, so the initial goal in this talk is I'm going to have this mix of driven dissipative physics. Things are going to be described by a Lindblad-style master equation. And if you don't love those the way that I do, I will spend one slide convincing you to love them, right? I'm going to be interested in what is the long-time steady state of the system undergoing all this dynamics. And I'm going to be greedy. I'd like to understand this dynamics without recourse to approximations. You give me this horrible equation that describes the dynamics. I'd like an analytic way of understanding what is the non-equilibrium steady state. How does it change as I change parameters? Could I have quantum features? Could I have interesting phase transitions? And again, the motivation is just to understand the fundamental physics. The motivation is maybe if you had these solutions, you could use them to benchmark numerical approximations. And maybe if we have this understanding, we can play with these different ingredients such that the steady state is entangled in an interesting and a useful way. Okay, and I'll define what I mean by that. Okay, so here's my one slide to tell you about Lindblad master equations and write the setting for the entire talk. I'm interested in dissipative quantum systems. So my system degrees of freedom will be coupled to some sort of environment. There are system operators that tell me how does the system couple to the environment. Here I've labeled these as Zs. And I'm going to consider this kind of, in a way, simple but generic situation where in some sense the environment is featureless. The environment has no correlation time. Its density of states is completely flat. So in this limit, the dynamics of the reduced density matrix describing the system follows this Lindblad or GKSL form. So there's a part we hopefully all know and love, which is just Hamiltonian evolution under the system Hamiltonian. And then the effects of the dissipation, the coupling to the environment, are in this funny second term here, right? With this super operator, there's a term like this for each of these coupling operators, okay? And if you've never seen this before, right, what's one nice way and one useful way to think about this equation? I could lump some of the terms in this dissipative part with my Hamiltonian, get an effective non-Hermitian Hamiltonian, right? And then I can write this equation as, well, it looks like I just modified the Schrodinger equation with a non-Hermitian Hamiltonian. That if you want, tells me about the, let's call it loss generated by the coupling to the environment. And then I have these extra terms here that you cannot lump with the non-Hermitian Hamiltonian. And I need all of that to conserve probability. So throughout this talk, I am going to assume the validity of this Lindblad master equation for a many-body system. One could question whether that's a good approximation for a particular system. There are lots of interesting things to say about that. This is not a talk that will get into those questions, right? So my starting point is, I believe this equation. I'm going to use it to describe my system. What does this equation actually predict? The other important thing, and I'll take the question in a second, I said I want driving, right? The way the driving is going to come in for everything I'll describe in this talk is within what we could call a rotating wave approximation. There is no explicit time dependence on the right-hand side here. The driving is going to come in either in terms of terms in the Hamiltonian or in these dissipators that can add and remove excitations. Okay? A lot of what I'll tell you can go beyond that regime, but I'll convince you life is already exciting enough, even if we treat the driving in this way. So I think Smitha had a question first. Yeah. So when you say mapping, do you mean going from this cartoon to this equation, or? Oh, so this is just, that's always something you can do. This is just a rewriting of this equation to maybe give a little bit of intuition on its form. And of course, there's much more that could be said about that, but you can always rewrite this like this. Yeah, yeah.
And then.
Yeah.
Give me some function.
No, so my goal is going to be, you come to me with some equation like this. I'm going to deal with the equation the way that you gave it to me and come up with some exact description of the steady state. Of course, this is not going to work for any system you can come to. This is sort of like if you want integrability or beta ansatz solutions, you're going to need to have a pretty special system where this works. I'm going to try to convince you there's a lot of physically, experimentally relevant systems that have the magic that enables these exact solutions. And it's not a one-hit wonder, right? I'm not just describing a way to solve one and only one system, and that's it. This seems to work for reasons we don't fully understand for a wide variety of different systems. Sorry, Marius, you have a question?
Yeah, so I ask these questions to all my friends and colleagues. Suppose you know the D part, right? The dissipative part.
Yeah.
And I know the steady states for that. Can you tell me if you add the H for another new steady state? Is there a formula to get the new steady state if I added the H hat?
So you know what the, okay, so there's a little bit,
D.
but you know what the steady state is without the D? Yeah.
Yeah, I know the steady state without the H hat. Now I add the, I mean, you could ask the question the symmetric way, but let's fix the dissipation and change H hat, right? Or add H hat. How do the...
So I think it's an interesting question. I think in general, you would have to tell me a little bit more about what the D terms are, right? If I just tell you some set of dissipators, it might not even be that there's a unique steady state.
Yeah.
Like, it would be fun to chat later. We are interested in versions of this inverse problem because it turns out to be very relevant to things like building Gibbs state samplers. But we're going to put more into the problem. We're going to use the time reversal symmetry that I'll tell you about. But it's a really interesting kind of question.
Yeah, I was just surprised that nobody has so far even studied that.
I think they've thought about it and tried, but I think you need to constrain the problem a bit more. But let's chat more. Yeah.
Good.
And by the way, please ask questions. I don't need to go through all my slides. Yeah.
We were talking about coupled environment, so I guess that you're including both dissipation and driving.
Yeah, so at the end of the day, I'm studying this kind of equation here. And like what I'm gonna, in these specific examples, what I mean by driving will be clear. The driving can show up in the Hamiltonian. It will show up with terms that correspond to being able to add and remove excitations, right? So imagine having a time-dependent Hamiltonian, but making a rotating wave approximation. So going into a frame where you get rid of the time dependence. So there could be driving in the Hamiltonian, but there could also be driving in this dissipative part, because it could be the environment can kind of incoherently pump my system with excitations. Okay, so all of that in principle could be living inside this equation. And what I'll tell you about will cover both those cases. Okay, so this is the one slide to get you to, okay, at least, if not love, at least accept Lindblad master equations. Very, very powerful tool, right? Here's a bunch of complicated Lindblad master equations, right? So what am I writing here? Here's a bunch of many-body systems. The dissipation in all cases is going to be loss. I'm not going to write down what the master equation is. I've written the Hamiltonian for these three systems. So this is a collection of interacting photonic cavities. The Hamiltonian is driving because the driving are these two-photon addition and removal terms. This is parametric driving or two-mode squeezing, right? So these kind of bosonic networks with these pairing terms and also some Hubbard or Kerr-like interactions. This is very relevant to a whole set of experiments, for example, in superconducting circuits. This thing here is a collection of two-level atoms that are interacting with one another. Here's like a Ising-ZZ interaction. And then they're also driven within the rotating wave approximation. So the Rabi driving of the qubit in the rotating wave approximation is like these X fields. The Z field is like a detuning. And again, there's dissipation and all of this. Maybe the dissipation is even collective. This is a dissipative version of a transverse field Ising model, okay? And here's another thing that is sort of like the Google experiment. This is a 1D spin chain where I have driving at the end, dissipation at the boundary. Okay, so what are you supposed to get out of this? These are three very different looking systems. They're many body. I could take the limit where there are many qubits, many cavities, whatever. They're not obviously trivial, right? They all have interactions on top of these Lindblad terms. What's the kind of surprise? For each one of these classes of models, there's a way to exactly solve for the non-equilibrium steady state. So you write down the Lindblad master equation for this guy, some set of parameters. There's a way where I can analytically tell you what the steady state is. And moreover, even though these systems look very different from one another, the way we get an exact solution uses a common element for all three. So there's a notion of time reversal symmetry, this thing we call hidden time reversal symmetry, that shows up in all three of these models without even fine-tuning the parameters. That funny symmetry enables these solutions. Okay, so the obvious next thing I have to tell you is what are those solutions, right? And this is the slide that always makes people angry, right? And so we'll see why that is. I'm not going to try to give a whole talk explaining and motivating and defining what this time reversal symmetry is. I'm going to give you the flavor of it, and I'm going to tell you about the physics that comes out of using it, okay? So the idea is, let's step back. How do I think about time reversal symmetry in a dissipative classical system, right? Simply playing the movie backwards of some motion and saying it looks the same is not the right way to do things, right? As you hopefully all learned in a stat mech course at some point, the more meaningful notion of time reversal symmetry in a dissipative classical system is the notion of detailed balance. Okay, so on the left here, I have a completely classical description of a system. So my classical system has different states labeled by this index J. They're probabilities for those states. A way to describe that classical stochastic or dissipative system would be what I'd call a classical master equation. So I have these probabilities, their rate of change are governed by some transition rates between these discrete states J and K. So what is detailed balance in the simplest form classically? Detailed balance says if you find a steady state of this classical master equation where the probabilities don't change, there's a kind of local constraint on that steady state. If I look at any pair of states, I and J, right? This kind of probability flux from I to J, this is the steady state probability, this is the transition rate. It's exactly balanced by the reverse transition, right? Start in J, make a transition from J to I. Right, so having a steady state just says, okay, I need some keys that make the entire right-hand side of the equation 0. Detailed balance is a much more strict kind of requirement where I'm constraining each element that generates the dynamics. Each pair of rates independently obey a constraint. So that's classical detailed balance in half a slide. How do I now think about quantum detailed balance? Okay, so the first thing is there's not a unique definition of quantum detailed balance. There's many, many definitions in the literature. I'm going to tell you one that is definitely not the most intuitive or obvious one, but it's going to be a useful notion. Okay, so my goal is now my quantum system is not described just with probabilities. It's described with a density matrix. I have my Lindblad style master equation. What is something vaguely analogous I can imagine doing in the quantum case I did in the classical case? Okay, so time reversal symmetry, right? We know time reversal symmetry involves anti-unitary operators in quantum mechanics. So what am I going to do? I'm going to try to come up with something analogous to this red box, put constraints on every piece of the generator of my dynamics. Okay, so what I'm going to do in the quantum case, can I find some anti-linear operator psi such that if I take the non-Hermitian Hamiltonian, which I introduced you before, take this H, combine it with some of the Zs, this psi sort of turns it into, this psi turns H effective into H effective dagger. And the same thing with these, what I'm calling jump operators, the things that tell me about the coupling to the environment. Psi sort of turns a Z into Z dagger. Okay, so this is just like a crazy definition, right? I'm going to say if you can find an anti-linear operator like this, I'm going to say congratulations, your system has what I call hidden time reversal symmetry. Congratulations, your system has this notion of quantum detailed balance. Of course, that's a definition, like why would I care about that? I'm going to enter that in 1 second, and I'll take the questions too. Just to make you not hate this definition, notice there's sort of a similarity between this condition here. These probabilities are sort of changing the I to J rate to the J to I rate. That's sort of like changing a Z to a Z dagger. And if I just made H effective here, H, and if the psi was anti-unitary, not anti-linear, but anti-unitary, that's the standard definition of time reversal symmetry for a Hamiltonian. Okay, so even though this looks weird, it's not completely crazy. It's not clear why it's useful. So why is it useful? If you can find a psi that satisfies all these constraints, one for the non-Hermitian Hamiltonian, one for each jump operator, then you immediately have the steady state of the system. So psi is an anti-linear operator. I can always do a polar decomposition. So pull out some anti-unitary operator. The thing that's left over is basically the square root of the steady state. Okay, if you want, if you find this psi, look at psi dagger, square the psi, that's your steady state. Okay, so this is my kind of, at first glance, wacky sounding definition of quantum detailed balance. What does it mean for your equation to have quantum detailed balance? There is this psi that has all these nice properties. That psi immediately gives you the steady state. Okay, so again, this still doesn't seem like, why would this show up in a real system? Why would this be useful? One hint at why this might be useful is if your system has this kind of detailed balance, the steady state, this psi, is highly, highly constrained. right? Because it has to satisfy each of these equations. So if your system has this property, the fact that it's so constrained often makes it very easy to find. Okay, let me give you a more physical way of thinking about this. Hidden time reversal symmetry in a non-dissipative classical system, you kind of can reverse the dynamics. Things kind of look the same. Well, it turns out systems that have this funny notion of hidden time reversal symmetry, there's something similar that goes on. But now we're going to reverse the dynamics, not in time, but sort of in space. Okay, so what do I mean by that? Here's another cartoon of my driven dissipative system. So my system is, maybe this is like a photonic cavity. It's driven, maybe the dissipation, let's just have one of these terms. Maybe it's loss. Okay? So when photons leave this cavity, the loss, they never come back. I can model that loss in whatever way I want. Let me model the loss where these photons go with a coupling to a fictitious chiral waveguide, right? So this is like a fictitious waveguide where photons can only go from left to right. As far as this real A cavity is concerned, that's loss. The photons leave and never come back. Okay, so now why is this interesting? Well, now I could put another system downstream that I'm calling the B system. Whatever I put here will not affect this system at all. Because look, the dynamics only takes things from left to right. Okay, so now it's almost like a purification at the level of the dynamics. In this doubled system, there's some bigger master equation that describes the physical system and this fictitious system. What I could hope for is, let me put something downstream, this magic B system, such that the whole thing, A plus B, relaxes to a pure state. Okay, if I could do that, that's great. I get this pure state. I trace out B. I have the answer I want. In general, this trick doesn't buy you anything. What the heck do you put downstream as the B system? But if you have this notion of hidden time reversal symmetry, then there's something very simple to put downstream. You just put a copy of the original system. So if this was a cavity or a bunch of qubits with some Hamiltonian, this is also a cavity or a qubit, a bunch of qubits. All you do is you flip the sign of the Hamiltonian and you couple to this waveguide the same way. Okay, so this is an idea that originally goes back to some nice work from Peter Zoller's group. We kind of extended it to this kind of many body regime. The upshot is this kind of perfect absorber setup where you can have your dissipative system coupled to a copy of it, produce a pure state, right? This is a more physical way of thinking about this kind of notion of hidden time reversal symmetry. These systems with this funny symmetry are those where there's something really easy to put downstream that, if you want, absorbs everything that's emitted by the first system, lets the whole thing relax to a pure entangled state. Okay, and this pure entangled state you get, if you decompose it the right way, you see there's a T operator here. That's the same anti-unitary operator I had on the previous slide. Yeah. I don't know if it's profound, but it's the heart of the trick. Yeah.
The first question, was it applied in any system or very specific?
It's specific. So this is like, that's the thing I was saying, the tricks I'm telling you, they apply to a lot of interesting systems. They do not apply to all systems. Yeah, absolutely. Yeah.
Where, for example, if you look at ENM problems, sometimes you have a certain bound condition, then you can put an image, something on the other side, and that solves the appropriate boundary conditions. So there's something in space like this going on here.
So full disclosure, like if you come to me with a system and ask me, is your trick going to work? The only real way I can answer the question is to try this construction and see if I get a pure state. And this is not as bad as it sounds. So often when you ask about, I have a classical system and I want to know, does it have detailed balance? The easiest way to check is to assume detailed balance and see if you can find a solution. So I wish I had deeper intuition as to be able to tell you what breaks this symmetry, what doesn't. That's something we don't actually have. So again, like in general, if you come with some Lindblad master equation, you can always do this, use the chiral waveguide to represent every dissipation. But in general, just putting a copy of the system will not lead to a pure state. There's something very special that lets this occur. I don't have a generic recipe for when that happens. Sorry, in the back, yeah.
Right, so this break seems like some sort of canonical purification, the specific pieces choice for the second.
Mhm.
So that's the canonical thing. So is your point that you can always find some like pairing Hamiltonian out of the Lindbladian equation that takes this as a graph state, or what do you mean by the trick here?
Yeah, so the trick, okay, so the trick is like even ignore this bit for a little bit. The surprising thing is that you can always represent all of the dissipation as coupling to chiral waveguides. The thing that does not happen generically is put a copy of the system downstream, couple it to the same chiral waveguide, just flip the sign of the Hamiltonian, and then magically the entire composite system relaxes to a pure state. So I'm not just doing a purification of the steady state density matrix, I'm constructing a simple dynamics that stabilizes that purification.
So the Lindbladian for this not double here. So what your construction is Lindbladian for the double state.
Exactly.
The pure state is the state.
Exactly.
Okay.
Yeah. And in general, this doubled Lindbladian always exists, but what you would have to put here would be horrible, and there's no easy way to get it. Here, the symmetry tells you there's something simple to put there. Marius, yeah.
So in math, all sympathetic for and that gives you, that tells you there has to be such a anti-symmetry. And it appears in high energy physics as the polar decomposition of modular. I mean,
They're different. So again, like this is an example of like a TFD state, like a thermofield double state. The fact that there's a time reversal operator there is important for such states. A more physical way of thinking about this T operator is in this purification of my steady state density matrix, I know what these square roots of P's should be, but I don't necessarily know what the phases should be. So for this absorber setup to work out, if you want, there's a special choice of the phases for these pointer states. Yeah.
But the thing is, if you have geometry, right? There's some possibility from geometry. That usually happens if you have something like a complex Nielsen, a complex structure restricted to real parameters. That's when this happens.
So I'd be really curious to chat more. I am not aware of any general simple way of ensuring this miracle will occur. But if you have thoughts, I would love to hear more about it. Yeah. Yeah.
So your state, decompose at this point, so you could sort of like invent a whole tower of dynamics based on like you can pure state, I just make up a tower operator, right?
So are you now asking about going in reverse? Yeah. So that's a really interesting question that we're kind of pursuing. So the short answer is yes, as long as you're allowed to have fairly crazy elements in the way each of the systems like couple to the two chiral waveguides. And one of the things we're interested in, along with other people, are there ways of doing this that respect notions of locality and give you something more reasonable? But yeah, that's a really interesting question. You could start by saying, I have a particular entangled target state. How do I go backwards? Right. And actually, that's even a little bit what the last little bullet point here is. So far, I've just introduced this doubled system as like a theoretical trick to be able to solve this master equation. But theorists have good friends who are experimentalists, such as Wolfgang, who know how to build things that I'm going to call a chiral waveguide. So now, if I know a setup like this that stabilizes an entangled state, you could use that as a recipe to build an experiment where dissipation will stabilize some non-trivial amount of entanglement, right? So these tricks are beyond just going, having a neat way to get exact solutions. there also may be a really interesting route to engineering non-unitary dynamics that leads to many-body entanglement. Okay, so I think that's all I want. Okay, there's a lot more general stuff I could say here, but I want to actually talk about some physics. So there's neat connections to the PETS recovery map. I see Marius, I had to mention PETS, right? I'm happy to chat about that more. Let me, like the last, how much time do I have, Wolfgang? 15-ish minutes. Okay, sure. So let me tell you a little bit about how this kind of, okay, crazy, kind of abstract sounding ideas shows up in some models that are definitely things people can build and experiment, and also reveals interesting physics. Like you might, we're always pessimists, right? Often as physicists. So you might be, you've got this magical trick, you can solve complicated many-body systems. Well, there must be some catch. So maybe the systems you can solve turn out to be really, really boring systems, right? So really, there's something really simple about these systems, and that's why this trick works. They're of no interest. Okay, so the first example I want to tell you is this driven spin chain example, where that is definitely not the case. If there's time, I'll tell you a little bit about this cavity QED setup, where we use these ideas to have a single platform where you just change drive detunings, and you can get all sorts of different entangled states. Okay, so here's a system without dissipation, condensed matter physicists love. This is the famous XXZ spin chain. This is a quantum information seminar, so I'm not going to talk about spins. I'll talk about qubits, right? So this is a 1D chain of qubits. Excitations can hop back and forth between nearest neighbor qubits. And also I have a ZZ interaction between neighboring qubits. Okay, so with the ZZ interaction, if you map to fermions, you get an interacting problem. So this is an interacting spin chain. It's an integrable spin chain, right? So there are fancier ways, the beta ansatz, to get insights into this system. Despite this thing being integrable, even without dissipation, there's been a lot of recent interest in asking, how do excitations move in this spin chain at high temperature, right? And there's, I would even say, still a debate. Is it ballistic? Is it diffusive? Is it subdiffusive, right? It's not a completely settled question, right? So one question or one idea is maybe I can study transport and more general non-equilibrium phenomena in this spin chain system by introducing dissipation. So how do I put dissipation in a way that lets me do transport? I have a sink. So I put loss on qubit 1, and here's my Lindblad dissipator. And I'm going to put driving at the other end of the chain. But the driving I'm going to put in is going to be in the Hamiltonian. It's coherent driving. This is like a Rabi drive in the rotating frame. Okay, so this is a system now. I've got a Lindblad master equation. The full Lindblad master equation is no longer beta ansatz solvable. Okay, so it's not one of those super special master equations you can get everything, but it has this hidden time reversal symmetry. We can solve analytically for the steady state. Okay, so how does the solution work? You do something paradoxical. You start with one complicated spin chain. You look at a system of two complicated spin chains, right? Here's the real chain. This is the fictitious one. I'm representing the loss here as a coupling to a chiral waveguide. The second spin chain has all the same parameters as the first spin chain, except I flip all the signs. Okay, and then the magic of this hidden time reversal symmetry is, I'm not going to go through it, we can write down an analytic solution for the pure steady state that this doubled system relaxes into. Okay, and there's a lot of fun things to say about this solution. It has the form of an infinite dimensional MPS. There's a really nice connection to a classical stat mech model. All we need to know about is we have an exact solution. We can use this solution to predict physically relevant quantities. Okay, so if we put on our kind of condensed matter or many body hats, what's the simplest thing I might hope for in this system? Can I have a phase transition in the steady state, like in this non-equilibrium steady state, as I tune parameters? And maybe the interesting parameters are the strength of the driving and how strong are the interactions? What's the ZZ interaction strength? So what's shown here for a system of 200 qubits from the exact solution This is the total density of qubit excitations. So the Z magnetization. So red being a half means they're like all the qubits are half excited. 0 means they're all in the ground state. As a function of the driving strength, again, just at the boundary, and as a function of this anisotropy or the interaction parameter. Okay, and what you see is there are phase transitions in this phase diagram. Okay, one of them I'm not going to talk about. As you increase the anisotropy past 1, you go from density to low density. I'm not going to talk about that because that's something that has a very close parallel to the physics of this XXZ spin chain if you had no dissipation. Okay, as you cross the Heisenberg point and go from easy plane to easy axis, the physics changes. So this is not so surprising. What's more surprising is this more continuous transition that I've sketched in green. Okay, and again, the exact solution even tells us, to a good approximation, what is this critical drive for going from a low density regime to a high density regime? Has this very, very simple form, right? And again, it really does have all the features of a continuous phase transition. Okay, so if I even do some finite size scaling, again, just varying the drive going through this, I get beautiful scaling collapse. So it really is a phase transition. There's some interesting physics here. Critical exponents change continuously with parameters. I'm going to focus on something simpler. What determines this green curve, right? This is such a simple expression. Surely this must be some simple property of the XXZ spin chain, right? So you think about the XXZ spin chain, you call a friend who's spent their whole life thinking about XXZ spin chains. This thing does show up in a closed, non-dissipative XXZ spin chain, but not where you might expect, right? So where does this show up? Imagine I had no dissipation, but I was trying to do a transport experiment. I'm trying to move charge or Z magnetization through this spin chain. Okay, and I'm going to do this at very, very high temperatures. I could imagine getting like a spin conductivity, right, from the Kubo formula. And at very, very high temperatures, because this is a integrable spin chain, there are quasi-particles, there's a piece in the frequency-dependent conductivity that is proportional to a delta function, right? So this is telling me, oh, there is a little bit of ballistic transport in the system. And there's this coefficient of how much ballistic transport do I have. What is that? It's exactly this critical driving strength up to a square root. Okay, so the kind of amazing thing, this non-equilibrium phase transition, this kind of dissipative physics, the value of this critical drive seems to be directly related to this thing where there's been a lot of interesting questions and controversy. How do I think about transport at high temperatures? You can even go further. It turns out there's a way of interpreting in the closed system this Drude weight, this d here, is kind of a velocity square. So if I think of this d as a velocity squared, this critical drive as a velocity, then there's a really, really crude classical way of thinking about the phase transition, right? Okay, I can make a reference to some stat mech model, ASAP. Let's just call it the traffic jam model, right? So think of a classical model where things are a bit different. Excitations can only go from left to right. They move at some velocity. If I pump the system very weakly, the excitations are going to speed through the system, disappear. I'm not going to have a lot of density. If I pump really hard, I'm going to get a pileup of excitations in the chain because they can't all get out quick enough. Okay, and again, this is the physics of the phase transition in this celebrated classical stat mech model, the ASAP model. Okay, so one kind of amazing thing is it seems like aspects of that physics are occurring in this fully quantum model, right? So this phase transition we're seeing seems to be related to transport phenomena. Okay. There's even more fun stuff here. If you take a vertical cut along this line, so I fix the drive, I vary the ZZ parameter, the interaction strength. It looks like there's noise in my diagram here, right? That's not noise. If I plot that, I see there's all these kind of resonances. This is now just with 15 spins. What are these resonances? They correspond to values of delta that satisfy this relationship here. Okay, so this is something that is known in the equilibrium system, that transport quantities are very, very different at these special values of delta, because the nature of the interacting quasi-particles are very different, This is very, very hard to measure in a closed system. This just shows up directly in the dissipative steady state. Okay, so the upshot is I want to convince you this model, I can solve it exactly using this hidden time reversal symmetry. This model is not boring. This model is not trivial. It has interesting non-equilibrium physics. This is also a model that's compatible with experiment, right? This is in the same vein as the system in that Google example I showed you at the beginning. Okay, as time is short, I'm going to skip this one other surprise about the model. One last, and Wolfgang, you can tell me when to shut up. Do I have 5-ish minutes, 10-ish? Okay, right. So when I motivated all of this, I said, hey, these ideas are more than just interesting ways to get exact solutions. Maybe we can use these ideas to actually engineer interesting entanglement, right? And so the way I solved that XXZ spin chain was to consider this double chain system where these two chains of qubits are coupled at the end via this one waveguide. If you really take the limit where driving is very, very strong, here's the exact solution. You end up with an entangled state that sort of factorizes into these kind of products of singlets. Okay, so this is something you could imagine might actually be useful. Maybe this is really a waveguide. Maybe these are two spin chains that are separated from one another. The claim is just using this common dissipation and these two Rabi drives, you could stabilize all of these qubits into this collection of non-local bell pairs. And so these ideas are not completely a theoretical curiosity. I think Wolfgang gave a talk last week, maybe, or sometime recently.
Yeah.
Oh, well, anyways, you can talk to Wolfgang more. Like the first experiment probing some of these ideas, just with one qubit here and one qubit here, but getting dissipatively stabilized entanglement is something that was just done recently in Wolfgang's group. Okay, and so I have 3 minutes left. Let me just, I'll sketch something very quickly that's a whole story on its end. Okay, so this hidden time reversal symmetry, we get exact solutions. This doubled system, you could build it like Wolfgang has. You can get a lot of kind of bipartite type entanglement. Lots of qubits here entangled with lots of qubits here. Could I get even more complicated kind of entanglement? Okay, and this is, I'm just gonna sketch this in a very heuristic way. You can bug me later. What if I want to use these ideas and get more than bipartite entanglement? So the idea is going to be, okay, I start with some system that has this hidden time reversal symmetry. It's exactly solvable, great. I know I can build this kind of dimerized system. So replace the dissipation by a one-way waveguide. Here's the system. Here's a copy with minus the Hamiltonian. And I know that because of this symmetry, these two things will stabilize into some dimerized entangled state. Okay, so if two systems are good, 2 times n systems are even better. So now I could just imagine just replicating that, right? To just in PowerPoint, take that cartoon, copy it in a row. So now I could have this chiral waveguide and then have lots of systems where I have a system H minus H, another H minus H. So by the same physics, this thing here will stabilize into an entangled state where these two things get entangled, these two things get entangled, these two things get entangled. And the colors here, this Hamiltonian, this one are all different, but the red hashed is the negative of the solid, the blue hashed, the negative of the blue. Okay, so that's an entangled state. It's still not the most entangled state or most interesting entangled state. So here's the crazy thing. What if I now permute the order of all my circles? So if you want, I'm introducing disorder into the system. So now this guy's partner is all the way at the end. This is H, this is minus H. This guy's partner is separated by this. So now it looks like, okay, you've just completely screwed things up. Why would anything good happen? The amazing thing is, at least in many examples we've looked at, you still get a pure entangled state out of this. But the pure entangled state is this simple dimerized state with some unitary acting on it. Okay, so it's as though with this dissipative dynamics, we're mimicking the physics of some quantum circuit. And here I've drawn it as a sequential quantum circuit, where you start with a bunch of pairs of dimers, you apply some unitary, you end up with a far more complicated entangled state. Okay, and again, this sounds like someone who had too much time on their hands and was playing with PowerPoint, just to give you a sense that there's something real that actually exhibits this physics. This is a fairly simple cavity QED system. I've got a bunch of atoms in a cavity, a collective Rabi drive loss through the end mirrors of the cavity that gives me collective loss on those atoms. If I now modify this system by changing the drive detunings for this group of atoms versus this, versus this, versus this, still only have this collective dissipation, and then put this funny all-to-all spin exchange term, this realizes this idea. So this setup here, which is very closely related to, for example, to an experiment in Monica Schleyer-Smith's group, just by changing the detunings, you can get very, very, very different pure entangled states. Okay, and I'm pretty much out of time. We have examples that are useful for metrology of delocalized parameters. We also have examples that are kind of fun from a condensed matter point of view. So in this system here, there's a way of picking the detunings. And you see here, the detunings all come in pairs, but this one's partner is all the way at the end. Right? There's a way of picking the detunings, let the system relax into its steady state. For this choice of detunings, and starting with each ensemble having a single qubit, you stabilize this paradigmatic state of a spin chain. You stabilize the famous AKLT state. So a state with symmetry protected topological order, a state that could be useful for measurement-based quantum computing. So now I'm out of time, right? Hopefully I've given you a flavor of these ideas, the fact that they're surprising, they're useful for exact solutions, maybe even for engineering interesting entanglement. And now I will stop. So thank you.
So we have already had a few questions. So
And I will just flash up the people who really did the work so you can.
So let's maybe
Yeah.
do it like that. Let's restrict ourselves to questions of people that are not coming to the launch. And everybody else should ask during lunch. How about that?
I can ask that, Jerry.
Yeah, so people have it. We had some projector issues, so we're really out of time. Anyone who is not going to the lunch and has a question, raise your hand. Otherwise, follow around to the lunch now. I think my power is.
What's that? Exactly.
Private numbers of triangle papers, implementation is still in that